welcome to our science show this year, and our Halloween is our theme. You'll see pumpkins around. Please do not try these demonstrations at home. So we're going to start off with a demonstration here. So I don't know if you guys have ever been at the school, like at night, any school. It seems a little freaky, right? Haunted. I know that I've been in Mr. Smith's room, and I've definitely noticed some sounds going on in there. But last weekend, I was actually here with some science teachers, and I stayed a little later, and I could hear some things in my room, and I was really wondering what was going on. And I realized it was coming from my freezer. So Casper likes to hang out in the freezer where it's nice and cold at night. So we're going to go ahead and open up the freezer. We're just going to let Casper out. Casper's hanging out somewhere in here. So, and what I've got over here in this fish tank is I've got some dry ice. And so dry ice is very cold. Negative. Mr. Wiley, want to tell me?
Around minus 95 Fahrenheit.
So about negative 95, right, Fahrenheit. And so Casper's jumped in here. So we're going to see if we can catch Casper. We're going to give a little, if we can find him here, maybe. Move him up. So Casper likes to go down the slide. And so when he goes down the slide, what will happen is he will blow the candles out. So let's see if we caught Casper. We'll see. He'll blow the candles out if he did. So there's Casper. And so now who knows? We'll let him back in the freezer because, you know, he likes the cold. So we'll go ahead and let him in there. So what's actually happening in this demonstration is there's dry ice in here. And dry ice, by the way, is solid carbon dioxide. And dry ice has a very unique property of skipping the liquid phase. So carbon dioxide goes directly from solid to gas. We call that sublimation. So you guys are used to hearing things like melting, boiling, condensing, freezing, those kinds of things. But there's another whole property called sublimation, basically, where we go from solid directly to a gas. So carbon dioxide happens to be a very dense gas. And so what's happening in here is, even though this container is open, the carbon dioxide will stay within the container because it's denser than water. And so what happened here is we collected some carbon dioxide and sent it down our ramp here, and so it doesn't disperse into the air like you would usually anticipate. And then carbon dioxide is something that we use in fire extinguishers often. So basically what it does is it kind of snuffs out that flame, and so that's what you saw here. So another pretty interesting thing you can do is you can see that the carbon dioxide is really in the container, and you can see that as you blow bubbles. And I'm gonna have to take my shield off here. So if I blow some bubbles into the container, you'll see it's a pretty interesting, unique thing that happens. So what happens is you can see that the bubble is actually floating. And if we sat here for a couple of minutes, what we would find is that the bubble will begin to shrink, or not to shrink, it will begin to sink down into the fish tank. And the reason that that happens is because the carbon dioxide is diffusing into the bubble. So sometimes you can get them to stay for pretty long. Sometimes they'll get a little frosty and frozen and sit there for a little longer. But it seems a little magic-like, doesn't it? Pretty easy to do. All you have to have is some bubbles for little kids and some dry ice and a tank to put it in.
Hi, I'm Mrs. Alvey. I teach biology and honors biology here. And I'm going to do an experiment here with you guys. And what we have are 3 cans with just a little bit of water in the bottom. And we are heating them. They're boiling, so you can see the steam rising. The liquid water, as you heat it, turns into water vapor. So that's a gas phase, and it's going to have really high pressure here inside the can with all of those gas molecules moving around really quickly. So let's see what happens if I dump them upside down into this ice water with dry ice in it. And you can just do this at home with regular ice water, but the dry ice is just for fun because it looks cool. So let's see what happens. Woo! Okay, so what happened was the air pressure outside the can was greater than the pressure inside the can because all of that water vapor got so cold that it condensed into actual water, so it imploded. Exciting.
I'm Peter Lindstrom, a science teacher at Roseburg High School. I teach physics and biology. And right now I'm going to be dropping some dry ice into these 3 beakers. Can you see the beakers? Something is going to happen, and Mrs. Brooks is going to explain what's happening.
And I'm Mrs. Brooks, and I teach physics to the freshmen, and then I also teach chemistry here at Roseburg High School. So what's happening in the first beaker is there was some bromothiamyl blue in there, and all of these containers have a bit of base in them. So they've got some soap in them, some water. We added a little bit of sodium hydroxide to the middle beaker. You saw that was a nice bright pink color as a base, and so you see that the color changes are going on towards the indicators. This is universal indicator, and so universal indicator is kind of our favorite indicator in chemistry because it goes sort of through that rainbow of colors process. And what we did is we added a little bit of dish soap in here just to add to the effect. Basically, you can sort of, take the bubbles and play with them, and usually we would blow them at you, but well, I have a shield on right now, so I can't. So anyway, kind of fun. We can come check on these later, but you can see the color change that happened. This sort of started off as a green-blue, and now it's turned yellow. This one goes from that bright pink to clear, and then this one started off as green in the beginning, and now it's getting more of that pinky orangey color.
I'm Chad Smith. I am one of the science teachers here at Roseburg High School. I am teaching chemistry, anatomy, physiology, and medical terminology. What we've got for you are some combustion reactions. So we are going to take some different alcohols. In this case, we're taking ethanol, and we are going to combust it with the use of oxygen. And we've created these type of cannons, if you will. This one here is made out of my favorite drink, Arnold Palmer's, half lemonade, half iced tea, best drink in the world. We've got our projectiles here that we've put together. We've got one that is a beaver projectile and one that represents the Oregon Ducks. Woo! Okay? So, so we'll start with the Oregon State Beaver. We'll put that in there. Ooh, I guess I better give some fuel first, huh? So like I said, the fuel that we're going to use here, we're going to use methanol. And what we're trying to do is to get that methanol to vaporize. And as it vaporizes, it turns into a gas, and then we can expose it to a flame. There we go. We can expose it to a flame, and when we do that, we should get a little bit of an explosion. Mr. Bartlett, if you would go ahead and light that. All right. We'll do that one more time. Let me put this, pour off the residue.
Mr. Smith, what's the residue?
Water. The gas that we create is carbon dioxide. That's what's going to, and then the pressure pushes that projectile out, and we produce water that I just ended up pouring down the sink. So let's see what we can do with our other projectile. We did that one. Where's our? Oh, we did do the Oregon Duck one. All right, so we're back to the Oregon State Beaver.
I have faith.
We'll get this shaken up a little bit, trying to speed up that process of vaporization. All right, Mr. Bartlett, if you would. Oh, it's going to be a dud. Oh, no.
I think it's fitting that it's the beaver.
Well, it's science. Sometimes things work, sometimes things don't. Our next one that we have, this is called a PCO popper. Just move back over here. On that PCO popper, what we've got is we've got a battery filler bulb that we've removed the actual top to that from, and then an ignition switch, which is a ignition switch for a gas grill. So once again, we're going to put our fuel source in there. We will put our ping pong ball or our projectile on that. We are going to help speed up that vaporization, move it around a little bit, let that vaporize, and
Woo!
all right. Come on.
And if we turn the lights on.
Hello, I'm Mr. Vince Aguirre. I teach physics and biology here at Roseburg High School. I'm going to demonstrate the egg in a flask.
So what's going to happen here is we're going to take a paper towel, we're going to light that paper towel on fire, and we're going to quickly put it into the flask and put the egg back on top and see what happens. Go for it. Well, you know, that's the fun of science, okay? This is why don't try this at home, kids. Oh.
Don't try this at home, yes.
And then put the egg on there. There you go. We're gonna watch what happens. We had a tough time finding a flask this morning.
Yes. Oh, not.
It's gonna need to be time elapsed. So what happens here is that the oxygen is being burnt inside the flask, and so once that is burnt away, it creates a vacuum in the container, and so the egg gets sucked into the flask. There you go.
Hello, my name is Mr. Weir. I teach ninth grade physics, honors physics, biology, and robotics after school. Today we're going to be playing with a vacuum chamber. In this case, we have normal atmospheric pressure weighing down on this balloon, keeping it quite compressed. As we remove the air, you'll see what happens to the balloon. So as you guys can see, as we pull more and more air out of the bell jar, we are getting the balloon to increase in size. My concern here is, any moment, our balloon is going to burst because we're going to suck a hole. Okay, so here's our nearly fully inflated balloon. The question for you guys is there actually any more air in the balloon now than there was when we started? I'm going to release the pressure. Release the vacuum. And theoretically, we have the same size balloon as before. Okay, this is our second experiment we're going to show you guys with the vacuum chamber. We have a regular, ordinary, yummy marshmallow, which has tiny, tiny little holes in it. And we have some, what is this, Barbasol shaving cream we're going to put in here. Cool. Okay, now we're going to apply a vacuum to this and see what those tiny, tiny little bubbles inside each one of these substances does when we remove all the air. Okay, I think we just keep getting bigger and bigger with the shaving cream. I'm going to turn it off here. And I'm going to release the vacuum and watch what happens. Does anybody want to eat a marshmallow? Okay, the last experiment we're going to do with the vacuum chamber, we have a container with regular water, and I think it says we're at about 30, maybe 35, 34 degrees. Normally water boils at 100 degrees at standard temperature and pressure. We're at Roseburg, so we're very, very close to standard temperature and pressure. As we decrease the pressure, the amazing thing is we can get things to boil at much, much lower temperatures, like room temperature. You may see this if you go camping at very, very high elevations. You try to boil spaghetti, and the spaghetti boils at such a low temperature, you can't ever actually cook your spaghetti. Let's see how this goes. Okay, as you can see, we are boiling water at 34 degrees Celsius. This is just like boiling water at a kind of a hot summer day. If you tried to boil your spaghetti in this, it would never actually cook.
All right, everybody, it's almost payday. I'm down to my last dollar. Sorry I didn't get you any candy. I'm gonna take this dollar and I'm gonna put it in this liquid right here. Mr. Weir has $100 he brought for me. We'll see if he lets me have it after I do this. So you might be wondering why I'm doing this, and sometimes I'll do this with kids' lunch money, so that's always fun. So instead I can do it with Mr. Weir's $100 bill. Apparently he is better at accounting than I am. Here we go. So what we're gonna do is we're just gonna take this dollar and we will light it on fire. So and that might be kind of scary, especially if I did a $100 bill. But what's happening here and what's in this liquid is rubbing alcohol and water. So I wouldn't suggest doing this with just rubbing alcohol. You probably want to add in the water. So a lot of people think money is paper, money is burnable, but really there's a lot of material in here, fabric in here, and so it burns at a much higher temperature. So I can sit here and do one of these, and basically it won't light on fire. What it is doing right now is it is evaporating the water away. I'm sure if I got it hot enough, eventually it would burn. But there you go, burning money.
All right, so this is Mr. Bartlett again. We're gonna mix a couple themes here, the theme of Halloween and also a little bit of chemistry. And we are calling this Frankenpickle. And basically what this is demonstrates, we're gonna plug this into the wall. We've got both ends of the wiring set up to each one of these nails that are inserted into the pickle, and the pickle is going to conduct that electricity much like our bodies do with the salts that we have in our bodies, and that energy is going to travel through those salts, and ions will pass through, and we should see this start to heat up and glow. So let's see what happens here. I hear something going on. Woo! Franken pickle!
All right, Mr. Smith back here. We are going to show you here, this is what we're going to call the fire tornado. In the Midwest, we're always concerned about tornadoes, and with what's been going on around here this last few months and all the fires we've gotten, we want to show you what happens when you put the two together. So we've got a fuel source down in here. We've created a little funnel with some mesh fencing, and we've got a Lazy Susan here so that we can spin this once we get it going. There it goes. So you can see, because of the mesh fencing, we create a vortex for that flame to travel up through. Got caught on me. All right.
Hello, my name is Craig Wiley. I teach chemistry and honors chemistry here at Roseburg High School, and we're here to show some demonstrations with liquid nitrogen today. Liquid nitrogen is a very, very cold liquid. Every day we're surrounded by air that's made of 80% nitrogen, but we can't see it. If you take that air and cool it down to very, very cold temperatures, around minus 300 degrees Fahrenheit, you can turn the nitrogen into a liquid, actually. And we've got some of that here. I went and bought some. It's here in this big cylinder. It's a big double wall cylinder, kind of like a big thermos bottle. And there's the liquid nitrogen. Right there. It looks kind of like it's boiling. It's because it is. We'll talk a little more about that later. I'll just dump some on the tabletop here, and you can see what happens with it. It doesn't really make the tabletop wet because it's not water. It just sort of spreads around and evaporates. Turns from the liquid back into a gas. All right. So there's a number of things we can do with liquid nitrogen. It is so very, very cold. I've got some here in this container already. We could dip a variety of things into the liquid nitrogen and see what happens to it. So let's take a dipper here. Let's put in a marshmallow and a couple of Swedish fish. Fish like to swim. So put a couple of fish in there, drop a marshmallow in there, and we'll check back on those a little bit later. All right. Some nice pretty flowers. Flowers for your weekend date. Preserve them. And those are ready. Now they're nice and preserved. But don't drop them. Don't drop them, because they tend to break with being frozen solid. Let's see, what else can we put in there? What a banana. What happens with a banana? And for a banana sickle? We'll just leave that in there for a little bit, and we'll check back on it a little bit later. We'll check back on our candy here and see how our marshmallows doing. Marshmallow and our fish here. It's all steamy in here. Oh, that's probably not a good idea. All right, the marshmallow's a little harder than it was before. I've never seen a marshmallow break like that. And oh, where's our fish? Fish broke already. Oh, it's got like, oh. So fish can break. Now we know. You can break the marshmallow and break the fish. Well, I've got a hammer, but we also may want to try something other than a hammer. This banana's gotten a little harder than it was. I wonder if we could use that in case we lost our hammer. That worked pretty well. Banana's gotten hard enough we can just hammer a nail with it. Not bad, huh? All right. Let's see, what else do we want to check on next? Ah, so I said that this is boiling. This marshmallow is, okay, the marshmallow broke up. It's gooey now. So we said that the liquid nitrogen is boiling. It looks like it's boiling. It actually is. And just to make the point that it really is boiling, I brought a tea kettle with me. Can something be so cold and still boil? It's boiling cold. Can we have boiling cold liquid? There we go. Boiling liquid nitrogen. All right, and let it boil for a while. Maybe we'll turn the sound off. Okay, next. So what happens when we put a balloon in liquid nitrogen? What happens when we put a balloon in it? Something's happening to this balloon. Doesn't take up quite as much room as it did before. Why would the balloon shrink and get so much smaller in liquid nitrogen? Think about it. What happens to air when you cool air? It shrinks and takes up less space. A lot less space in this case. So we're taking up a lot less space than we were before. And we can put those whole long, 3-foot long balloons in liquid nitrogen. It's kind of fun to watch them grow and come back to life again. Like that one sprung a leak. That one died. All right. We can do the same thing with round balloons. Get the same effect. Balloons can come back to life in the same way. The collapse right down to nothing. There's no volume left in this balloon. All right, now finally, one of the other last things I want to illustrate with liquid nitrogen, I hope, and this may or may not work, sometimes it does, sometimes it doesn't, is this. Now liquid nitrogen, as I said, has a boiling point, that's what it's doing, boiling right now, of around -300 degrees Fahrenheit. Oxygen has a boiling point that's about 20 to 25 degrees higher than liquid nitrogen. So I put some liquid nitrogen in here a little while ago, and I put a really strong magnet here in the liquid nitrogen. Why am I doing that? Okay. Honors chemistry will relate to this perhaps the best. We started talking about Lewis dot diagrams. There's a Lewis dot diagram for an oxygen molecule. An oxygen molecule, like we breathe in the air, is actually two oxygen atoms joined together with a double bond. And in the Lewis diagram, we see the double bond there. Outside of that double bond, oxygen has other pairs of electrons that are not involved in bonding. Some of you may remember that there's a characteristic of electrons called spin. Those electrons can have different spins on them so that so the oxygen actually ends up being somewhat magnetic. It exhibits something we call paramagnetism. So the idea here is that some of the oxygen from the air will have cooled to a point here where it's turned into a liquid at the bottom. Now, liquid oxygen is virtually clear, much like liquid nitrogen. So what I'm hoping we can be able to see here is that on the very bottom of this magnet, we'll see a tiny residue of liquid oxygen when it comes out of here. So I'm going to lift this up and tip it towards you. And if you see any liquid on there, it's not going to be the nitrogen. There'll be a little bit of liquid oxygen right on the bottom. So sometimes you can see it, sometimes you can't. That's okay. All right. So liquid nitrogen, good cold stuff. Want to be careful when you handle it, protect yourself, and enjoy chemistry.
All right, good morning, everybody. My name is Mr. Bartlett, Bill Bartlett. I teach chemistry and forensic science, and we've got another combustion reaction, but we're also going to demonstrate a little bit of Newton's third law of motion, which says for every action there's an equal and opposite reaction. So we've got methanol inside of this container, and we are going to ignite that, and we call this the whoosh bottle. You'll hear a little sound, but you'll also see that as that gas is ignited and heated up, it wants to vent out, and it'll vent out this nozzle and go in that direction, causing our whoosh bottle to go in the opposite direction, supporting Newton's third law. So I'll get some help from Mr. Smith here, see if we can ignite this. Here we go.
Right, hello, Mr. Bowen again. This is a nice jack-o'-lantern here, but it needs more. It needs more. So let's. Yes. All right.
What are you putting on the jack-o'-lantern?
I'm gonna. This is special fuel, ethyl alcohol. It's.
Don't be greedy now. Don't be greedy.
Oh,
Here we go.
okay.
Oh yeah. Come on, Mr.
Okay.
Bowen.
We want to talk about the other uses of this.
Yeah.
Try low, too.
Okay, yeah, burn up.
It's starting to go. Hey, look at the top, Mr. Bowen. The stem was a little dry.
Sweet. Let me do the pan around.
You can see it's dripping down, and as the drips fall, the flames fall with it. It's pretty cool.
Hi, Mr. Wiley again here. What I want to show you now is what happens when atoms are giving off energy. We've talked a lot about electron configurations in chemistry class and advanced chemistry class, and we're going to transfer that knowledge over now to the production of light from various atoms of metals. First though, I want to point out something for you that you're already really familiar with. When you run electricity through neon gas, it makes this familiar bright light. That's because the electrons in the neon gas are being excited, boosted to higher energy levels. They stay there just for an instant, fall down to lower energy levels, and release light. So when we run electricity through atoms, that can happen. But there are other ways we can heat up atoms as well. Take this, for example. I've got a little bit of common sodium chloride here in the dish, and I'm going to light this burner, and we'll use heat to excite the atoms this time. So I'll wet the end of this little metal rod here, stick it to some of the sodium chloride salt, and then we'll put that in the flame, energize the atoms, and see what happens. Whoa, we got that really bright, intense, orangish yellow flame. So you might recognize that orangish color as being the color of some of the parking lot lights that you see, or lights on the side of buildings at night. So some of those lights have that same orange color because they use sodium gas. And when they run electricity through sodium gas, it gives off that same color. Now, another thing we can do is take salts of some of the metals and heat them with flame and see what colors they give off. Sodium has that unique orangish color. Neon has that bright reddish orange color. But each different metal gives off its own unique color pattern. We have sodium here, we've seen that already, copper, potassium, strontium, and lithium. So I'm going to turn this flame off, and we're going to put a little bit of fuel on each of these so that they'll burn. So a little bit of fuel, and then we'll ignite them, and you can see the different colors. Some of these same colors that you see will be the same colors that you see in fireworks, literally using these same chemicals. All right, we'll let that fuel burn a little bit, and we should start seeing some colors showing here. All right, there's copper. Copper has a classic bluish greenish flame in it. There's that bright orange of sodium. Potassium with another kind of an orangish yellow. That strontium flame is beautiful with that rosy orangish color. And lithium with that deep scarlet reddish color.
Hi, I'm Mr. Bowen. I teach science. I teach biology, environmental science, and physics here at Roseburg High School.
My name is Mr. Weir again, and we are going to show you the Van de Graaff generator. The Van de Graaff generator kind of works like at the winter time, you're going across the carpet with your socks on, and you're building up that static electricity, and you go up to your little brother or sister and you touch them in the ear. That little shock is what is building up in this little dome. We've got this belt that's collecting those electrons and building them up here. We have a super, super cool thing to show you. When we turn it on, we're going to put these little aluminum pie plates, and some electric magic happens. That was the best part of the whole thing. Okay, we're going to do a very similar experiment, this time with little paper dots. And when we put the paper dots on the top of the Van de Graaff generator, they're going to experience electric.
Here we go.
Okay.
Go ahead.
So, this is Mr. Vincegara again, teaching physics and biology. I'm going to attempt to get the electrons to move through this light bulb. You go ahead and turn those on.
Yep.
Thank you very much. So, it's doing an excellent job of going through me. But as you can see.
Say it's my shoes. I
Yeah,
have
your
another one of
shoes are
my
an issue.
So it's going to discharge to that.
Oh, she's...
I'm very electrical. I don't know why.
Oh! Woo! That is awesome. Miss Brooks, you are the winner. Awesome.
And then
Okay,
you can
good.
do one of these, see?
Uh-huh. Cool. Okay. Hey, this is Mr. Weir and Miss Alvey back. We have Miss Alvey all wrapped up in a big plastic bag. You can't see it from there, but we have a shop vac here. We are going to evacuate to remove all the air. This column of air on top of her is going to press that plastic bag against her, trapping her so she can't even move. Ready, set, go. How do you feel, Miss Alvey?
I feel pretty good. Pretty comfortable.
Hi, here we go.
It actually takes my breath away.
Does it really?
It does. It
That's awesome.
Started.
Hey everybody, it's Mrs. Brooks here again. So this demonstration is to show you how many calories, how much energy is in a gummy bear. So think about eating a little itty bitty gummy bear like this. You probably don't think too much about that, but the energy that's stored in this little gummy bear is pretty incredible. So what I've got here in this test tube is potassium chlorate. And so what I'm gonna do is I'm gonna heat this potassium chlorate up, and I'm going to get it all melted. And then what I'm gonna do is I'm gonna put a gummy bear in there, and it's gonna show the amount of energy that is in a gummy bear. And I might try to get 2 in there. But we've got to start with getting this potassium chlorate melted first. So now what I'm gonna do is I'm gonna put the gummy bears into the test tube here, and we're gonna watch what happens. So as you can see, this is another highly exothermic reaction, and it's probably pretty surprising to you to see how much energy is stored in a gummy bear. So the next time you want to eat an entire bag of gummy bears, you might want to think about the calories that you're going to have to burn through exercise after that. So this demonstration is called the puking pumpkin. So inside this pumpkin, I have a little dish that has some hydrogen peroxide. It's not the hydrogen peroxide that you can buy in the store. It's lab grade. It's much stronger. And then to that, I added a little bit of food coloring and some dish soap. So what I'm going to do is I'm going to dump in this potassium iodide solution, and we're going to see what happens.
Woohoo!
All right. So this is a highly exothermic reaction. If you look at it, there's lots of steam. There's endothermic and exothermic reactions. So exothermic releases heat. What's happening here is that the hydrogen peroxide and the potassium iodide are reacting and creating a bunch of oxygen gas. So we put dish soap in here to blow those bubbles up, so you get your puking pumpkin.
Okay, on this experiment, we're working on Bernoulli's principle. This is the same principle that works on wings of an airplane. As you push air over a curved substance, you get a high pressure here, low pressure here, and it lifts the ball. So let's see if I can do this right. So the first experiment, we used this straw and this itsy beansy tiny ping pong ball, but as you know, bigger is better, so we gotta try to do it bigger. So we're gonna try with this slightly larger ball and a monster leaf blower. Here we go.
have here, guys, we're looking at a set of cow lungs, and we're going to use a shop vac to go ahead and inflate those. And the whole premise behind this is we want to show you how those lungs inflate on top of the fact of what's going on in there as we're going through the process of diffusion, and we're taking and moving oxygen into the capillary beds that surround the individual, what we call alveoli of the lungs. And in the same process, carbon dioxide is leaving your blood supply and going into that empty space within the lungs to be exhaled on the breath out. All right.
They'll get way bigger. So on this side, they're popping out on this side. Anybody want to touch it?
Okay, go ahead and turn it off and watch it collapse.
Ooh. That was hard to hold it. Ew.
Hey, Mr. Wiley here at Roseburg High School. We have a demonstration here related to what happens when dissolved gases are suddenly released. We don't really think about it very much, but water has dissolved nitrogen and dissolved oxygen in it. And when it comes to something like soda, we have dissolved carbon dioxide in it. When that carbon dioxide is trapped in the bottle under high pressure, it stays dissolved. But if we release that pressure suddenly, then the bubbles come out very rapidly. If we add something to the soda besides, then those bubbles have a place to gather and form little gas nucleation centers. So we're going to add some Mentos candy into this Coke, and when we do that, it'll provide a large surface area for the rapid formation of a bunch of bubbles. See what happens. Thank you, Mr. Bowen.
Mrs. Weber, and I'm the principal here, and I'm pretty excited to get to do the science experiment with you.
And I'm Mr. Wiley here with you again. We're going to take a look at what happens with methane combustion right now. One of the common fuels that we have in our home is methane. And we have piped in methane gas, natural gas right here in the classroom. So we're going to turn on the methane gas and just blow some bubbles with it here in a soap bubble solution. Get a nice column of bubbles growing up there. These are not air bubbles, these are methane gas bubbles. There. With it being methane gas, they are flammable as well. So we have a couple of other assistants here with Mr. Bowen. Mr. Bowen's going to be our flame provider, and we'll see what happens with the methane bubbles.
And Mrs. Weber's going to put her hands really flat, thumbs down.
All right, Mr. Smith back here. We're going to do a flaming or a spitting fire pumpkin here. What we're using to do this is we are going to use a organic substance called lycopodium powder. Lycopodium powder is a spore, and it is very, very fine particulate. For those of you that have been in the area for a while, the fire at Murphy Plywood, that was because the dust in the vacuums in that facility, that dust got into the air and a spark ignited it. Same thing happened in Springfield about 6 years ago when they lost their mill. Anything that gets into that fine powder has that ability, when a spark's added to it with that increased surface area, to combust, and combust quite violently. So that's what we're going to see happen right here.
Demonstrate another experiment again using lycopodium powder, except this demonstrates kind of what happens in the Midwest. There's oftentimes grain elevator explosions where they've got those big silos full of grains, and again they start to develop dust, and if there is a spark, just like we did with the pumpkin, it will ignite and cause an explosion. And so in this particular case, we're using a can. We've got lycopodium powder at the bottom and a candle as our light source, and we're going to blow the lid off of this can.
That's all, folks.